All right, good morning, everybody. Thanks for, hi, Curtis. I got some friendlies. I planted them for questions, so should be good.
Are we there yet?
Yeah. Thanks for coming to my talk. It's entitled Build Your Own Core Adapter, Universal Core Adapter for Fun and Profit. I changed the subtitle because this is more accurate. Like write, copy, abstract. And that's something I apply to almost all of my code and when I'm solving a problem. I'm Miah Petersen. I work at ZSuite Tech. I'm in Austin. We're fully remote, so got just like everybody else, I think. My team's name is Banana Pants, and we handle all of the information transfer between the banks and us. What we're going to be talking about today is how we're moving away from the batch transfers to the live transactions. And the talk is really about solving the problem with good programming fundamentals. There's no magic here. There's no snake oil. It's just we happen to be able to break apart our problem in a way that makes it very easy for us to build new ones. I'm going to talk about what we replaced. I'm going to talk about what we actually built, and then some of the things that we gained from this architecture. ZSGrow, that's our main platform. It is a sub-accounting system. It's a sub-accounting ledger. If you haven't dealt with sub-accounting, the classic example that we talk to our banks about are landlords. So a landlord has 100,000 units. They need to keep track of the security deposit for each of those units over the course of a year. They need to know how much money is paid in interest over that year or years. They need to be able to know what fees they can assess against it, and it varies from state to state. So the big old circle here is a single account on a core, and then each one of those pieces of the pie is a sub-account, and that sub-account will have a different beneficiary who is going to get a W-9 at the end of the year for the interest that they earned. That's like the primary use case, or that's the one everybody knows. There's and for these landlord, the overnight systems are fine. Like doing a batch file and having it reconciled the next day is totally okay. But there are some use cases like the 1031 exchanges that need a real-time process. And if you haven't heard the 1031 exchange, that's a way. So say you have a property that you bought for $5 million, you want to buy a new property, so you can sell that property, put it in a 1031 exchange, and then as long as you use that money to buy the new property, there's no tax. So it's a tax minimization strategy. The original method that we started with was batch files. The transactions for our consumers or our users, they build up through the day, and then at some cutoff that's determined by the bank, those transactions get sent to us and turned into a file, which we then send to them, send to the bank, and the core processes it overnight, and then we get another file the next day that says, these transactions have reconciled, and it works great. Like we support a couple proprietary formats like ATE for FIS and FISOR Premier. We had a client that wanted JSON, so we built that. And then Notch is the big one, because was it trillions of dollars a day is processed via SFTP? That's like a crazy statistic. This is a C4 diagram, just like system context. Right? From the consumer's perspective, they say, hey, I want to open a sub account to the ZSGrow system. ZSGrow system ultimately sends an SFTP to the bank core. Core does the transaction. Like real simple. Under the hood, it's a little bit, it looks like this. The customer's hitting the container, which is our ZSGrow API. As it builds, once it hits that trigger point, those get transactions get sent into an AWS message queue, which then is picked up by these lambdas that they grab all the transactions, they create the file, they drop it in the bucket, and then the bucket sends it on to the core. So we're going to replace this batch system, which is a minimum of 24 hours of process time, with something live. So we looked at the problem, and the key things that we need to do you need to be able to send transactions, and there's two kinds of transactions that we need to be able to send. We need to be able to move money from a DDA and a DDA or SAV to SAV or some combination thereof, and we need to be able to make interest payments because we are the record of truth for the sub-account interest. So these holding accounts, these DDA accounts where on the core, their interest rate is set to 0, and we're actually doing all the accruing in our ledger. To do that live, we also noticed that we also wanted to do a live balance check so that we could confirm that, yeah, your money is there, and you can do the transaction. And then the final design piece or design constraint is that we needed it to be able to work in our existing structure. So we built a monolith, right? That's the fastest way to get your code up and running and working, and then you can actually test against it. We built a fast API HTTP server. So each endpoint is, there's an endpoint for transfers and there's an endpoint for balance checks. We're going to deploy this out across Kubernetes because that's where our API is. And that was a real easy way for us to get it up and running. And the API isn't going to notice any change. The one change that the API is going to make is instead of building up those transactions through the day, it's going to just start sending them to the AWS SQS queue as soon as they happen, which we will then pick them up and route them to the correct endpoint. Just a quick directory. Look, it's just there's the API, there's a config, there's models, and then you should always have tests. Which, yeah, you should always have tests. Here's the original, the same C4 diagram of the system. You'll note the one difference is that instead of SFTP, we're making API calls, right? Under the hood, the container that was a series of lambdas that I didn't go out is now this core adapter. And the core adapter is made up of this web server, which is that fast API, and then this core model, which is, that's the actual thing that talks to the bank's API. There's a little black box for Argo events, which was how we were sending transactions from the message queue back to the web server in Kubernetes. Our first implementation was on Fiserv DNA. Has anybody integrated against Fiserv DNA? Actually, oh, there's one. Has anybody integrated against any of the core APIs? Just, okay, all right. So there's no documentation on DNA. In fact, the engineer that we were working with at Fiserv sent me a CHM file that had nothing in it. It had a list of endpoints, but there was no content. It was silly. But they kept their documentation locked down. He told me that sometimes he couldn't even get to his documentation without the correct biometrics and logins and multi-factor authentication. And with them in particular, we were not Fiserv's client. The bank is the client. So all communication had to go through the bank and DNA at the same time. The developer or the engineer at Fiserv was wonderful. They always answered questions. They always they gave us exactly what we needed. They were able to offer up advice on which endpoints and what's the best way to structure it. We thought we were going to get, they have two APIs. They have a RESTful API and a SOAP API. And we thought we were going to get to do REST, so we built the whole thing in REST, and then we got to the interest payments and found out that their REST API didn't have the capabilities to do interest payments against the GL. So that was a fun surprise. So we implemented that in SOAP. And at one point, we had, we just did the transactions endpoint in SOAP. And we left the balance in the REST API, which meant we had two logins, so we had multiple paths, which we decided that was a terrible idea, and ultimately threw out everything that was in the REST API implementation and went purely with their SOAP. Oops, wrong way. And this one took about 9 months. There was some back and forth that was specifically, this has a VPN, and so there was some learning there of how to set up AWS with VPN so that we could have redundancy, we could hit their correct data centers, because I think we're sending it to 2 different specific data centers. But it was fun, and it was 9 months, and at the end of it, it was real time. Oh, DNA is actually a real-time core. And when I say that, I mean you send a transaction to DNA, DNA moves the money immediately, sends you back a unique transaction identifier, and you're done. You're good to move on. Not all cores are like that. We'll talk about the overnight cores in a second. All right, so that was write. Write your first code. Do it. You have a working one. It's great. The next one, we're just going to copy that folder over. And rename wherever we see DNA. We're going to move it to communicator open because that was our second one. There was no difference on how we do the deployment, how we do configuration. It was a very simple thing. I cannot tell you how excited I was when we saw public documentation. It was awesome. And this one was mostly RESTful. We were using Communicator Open against Premier. Communicator Open is Fiserv's wrapper. Is their newest wrapper on top of all their cores, which is what in a perfect world, I don't want to have to write these. I want to use one service, one unified API, one schema does everything. But that does not exist. And even Communicator Open, they have the endpoints stay the same. So you'll be hitting, I don't know, something / transfer. But the JSON payloads for their individual cores are different. So this was against Communicator Open Premier. It took us 5 months. Has anybody been on a call with Fiserv? They bring a lot of people. and they will chew through their budget as quickly as they can. So that's all I got to say for that. All right, so we built these 2, and now it's actually time to abstract out what we've done so that we can turn this into more of a factory and less of a one-off solution. The things that we noticed, there's a clear fracture plane between the messages and transactions that are coming out of our API and what we need to send to the model. So we were able to, let's see. Right, so that the adapter is made up of two things. We'll get to that in a second. Okay. Yeah, there's some helper functions that we built, for some APIs, you're doing a transaction, which means you're actually saying this is a debit to this account, this is a credit to this account, and that's whereas a transfer, where you're saying move money from account A to account B. And it varies from core to core and API to API. Typically, you can't do a transfer for a GL, so you actually have to build your transactions for, like, if you're doing an interest payment, the holding account, you're going to say, credit this holding account $100 of interest, debit the GL for that $100. And if you have to do that, there's always transaction codes. Most of the time, the bank knows what they are. Sometimes the banks have to create them. It really depends on who you're talking to. The core adapters all have to do 3 things. Well, initially they just had to do 2 things because we got lucky, or we thought everything was going to be like DNA, where you would do a transaction, you get a unique transaction code ID, and you know that as long as you can get that back the next day, you know it's reconciled. But ultimately, we will need the search counts transaction history so that you can do some item potency checks. The directories stayed the same when we started switching this out. But we moved to a, let's see, we're going to move it to a model. This middleware, which was Fast API to begin with, like it's its own module or library. We wrote it. It lived next to all of our core implementations, and inside of that library there was also a model of the base model. The middleware, it really just handles all the inputs and outputs out of the API. So if the API and that contract is basically fixed. We know what a transfer looks like. It's got 2 account numbers, it's got our unique identifiers, it's got the amount, and the type. So when it hits the middleware, like this would be the /balance endpoint that would be hit from Argo events with a balance event, and it's up the model, the core adapter inherits from, wait, no, that's not right. I'm talking about the middle. All right, we'll go back to this. It's version. So as we update this, like let's say we're going to add item potency, you would just install the newest version of this library, and then you have item potency ready to once you implement it in your model. This is the initial base adapter model, which was what I was starting to talk about too soon. So the balance endpoint, that handler, just calls model.balance and passes in that balance event. And you take this adapter model as you inherit from it, and now you can build a adapter that the middleware can talk to without any extra information. For the transfer, that transfer event could be a DDA to DDA. It could be a DDA to interest to, or a GL to interest, GL to DDA. We don't know, and the middleware, it doesn't care. It's just going to pass that event down to the model, and then it's totally up to the model to do whatever you need to do your transfer. So the next one we implemented was JExchange, and they also have public-facing documentation. They respond really well if you have questions for support. It's SOAP. It's not my favorite, but it's fine. They have a fun vetting process. You have to have a sponsor bank. You build with the sponsor bank. Sponsor bank has to, after you deploy to production, the sponsor bank has to use the system for a month, and then they sign off on it. Once they sign off on it, you can now deploy this out to anyone, any bank that uses JExchange. Since it was the first one, we created a folder, but instead of copying the folder, we just installed the base module. Then we took JExchange and made the JExchange model and inherited from that base class and started implementing against implementing those two routes, or two functions. I want to say that they have a transfer route, so moving money through DDA to DDA was simple, and then they had a slightly more complicated GL interest transaction. And this one took 3 months. So timescale is dropping. Oh, we've only done it against Silver Lake on this one. So then we did FIS Code Connect, and FIS, so the IBS, and this is specifically IBS. IBS is real time, but they don't return a unique transaction identifier, which is infuriating, because they have one, but the API doesn't actually return it. So if you want to do item potency here, you have to be able to go get to transaction history, scan through all the transactions, look for the one that you think you're supposed to be processing right now. And you make a good guess, and then you check tomorrow. This was the first one that we had, there was an API gateway that we're hitting, but you're also sending in your core. You also have core credentials, which sort of throws back to something I learned two DevCons ago when the Jack Henry CTO was talking about how the architecture of the core is a teller. There's a teller who is doing one thing at human speed at a time. And so we have a teller credentials. They suggested actually that you have 2 sets of core credentials because the IBS core requires those core credentials to expire every 90 days, or your password expires every 90 days. So we have one set of core credentials that we're using in even months, and the ones that are dormant, we change the password that month, and then vice versa. So it's a fun cron job that goes off. For IBS, it took 1 month. Their documentation is almost public. You can go to their documentation site and you can see all their cores, but as soon as you click on a core, it's hey, you got to request access. So we built, they give you Horizon for free, maybe? No? Okay, that's my CTO. We got Horizon first, even though we weren't immigrating against it. And then they gave us IBS. But for giggles, we had a contractor do the Horizon one as well, since we already had access to it, and we do know that there are banks that are going to be interested in it. And it took 2 weeks. Or, almost everything after this is in the 2 week time frame. Which that's just mind-boggling to me. Oh man, I wish we could use Q2 for everyone, just because they do offer somewhat of a unified API. I will also say that every time we've implemented against Q2, something has gone wrong, and it's all been in wildly varying ways. Most recently, for this adapter, the bank that we were implementing against was for this uses the Smiley core, and in Q2 they have 2 ID fields for an account. There is an internal account number and an external account number. If you've ever worked with a credit union, the internal account number is something for a savings account, it's S007. And then the external account number is the actual, you would use the routing number and that account number to send money, right? And that external account number in every other bank core that we've ever dealt with at Q2 has always been that checking number, basically. With Smiley, it's some random GUID, like just no idea. And the internal number is the actual account number. And Q2's SDK has no way to simply look up by the internal number. I filed a ticket. A couple days later, one of their lead developers picked it up and was like, oh, this is definitely something that we can do and should do. He worked on it, and then like, I don't know, it took him, it was like 2 weeks, and then he told me that he's just waiting on the DB team to vet it, and then it'll be in the next SDK, at which point we'll be able to do Smiley, as well as any other account or any other core that does a similar shenanigans. Let's see, the first core that we implemented against these guys was Fiserv Premier, but they use Communicator Advantage, which is the older version of the Fiserv wrappers. And we couldn't do a interest transaction through the base level SDK, but they have a way to do a pass-through, so you can craft your own payload and send that on to onto the core, which was great. When we implemented the DNA version, like Q2 on top of DNA, the adapter there couldn't go to the GL transaction, couldn't create any GL transactions. So that bank has to use what we call a shadow account to pay interest. Smiley can't do that. So for every bank that we implemented with Q2, like one caveat is you're probably going to use a hosting account or a regular DDA account that the bank owns to pay interest. Let's see. I think I'll probably remember some more about Q2 and I'll come back to it. So your bank doesn't want to give you access to their core, but they have their own API. Well, that's fine. As long as they have an API that we can hit, like, we will generate that for you. Like, these guys also, the bank that did this, they also they didn't want to send us any of their account numbers. They actually want to tokenize all their account numbers so we get some random alphanumeric that matches to it. And I mean, we don't care. We will gladly implement against that if you give us the data. And as long as you give us good as long as you give us good documentation, which in this case was like PDFs that they exported out of their Confluence, like, it works. The diciest thing here was like they decided halfway through that they wanted to deprecate their authorization, the way they were having us authorize. And we're like, oh, okay. I guess we can do it a different way if you need. It totally works for us. And this one was 3 weeks. And that was mostly just going back and forth with them about like how we're going to authorize with you. The final core that we've implemented against so far is COCC. And we don't have a COCC customer, but we have a contractor. We don't have one that's signed up for real time yet. But we have a contractor for 3 months that's been doing this, and we need him to work, so we made him build the COCC one for us. It was fun. It was nice. I didn't have to worry about it. It's the architecture has been such that we can hand the documentation off to what is essentially a junior or mid-level developer, and they just build the model and hit the APIs. When I sent my presentation to the people at Moov, they were like, "Hey, can you add something about what you would do different?" And well, we didn't like the way we deployed the architecture, like the deployment architecture. It was expensive. In Kubernetes, like am a huge proponent of Kubernetes. I love deployment by configuration. I love saying, hey, I need a deployment with 5 pods running this and whatever the sidecars are, and then I don't have to think about it. I feel like every time I've needed a programming instance of, I don't know, like cron jobs. I needed cron jobs. They then came out with a cron job. Whenever I need something specific, the community seems to have popped up with what I need. But all of the communication to our core adapters is asynchronous, so we don't need a API that's running 24 hours a day, 7 days a week. Doesn't need to be up at 5 nines. Cold starts don't matter. As long as they're getting, the only time it matters at all from a real-time perspective is the balance call, because they need to be able to have a balance to run a transaction. And so as long as that's running and takes less than 5 seconds, then they are okay. These are not, well, maybe they are anger button pushers, but they don't seem to be. So we're gonna, that Argo events, that was our initial implementation, which also upped the cost because as a tenant-based system, we had to run all the containers for a event bus, which for Argo events is like there's a controller, there's 3 event bus containers, and then there's sensors as well as there's a, I forget what the other one, maybe a trigger, which pulls the information from wherever however you're filling the queue, it's filling it up. So that's like I don't know, 6 or 7 different containers in our Fargate cluster that's just, and multiply, so there's multiply that by 100, so there's 700 of these. That's just eating dollars for no good reason. We also found that we actually couldn't rate limit in the way that we needed to. So all that led to us moving it to a Lambda. Because of the split, it actually, the move was very easy. We wrote a new middleware. This middleware, instead of having endpoints, it has handlers. When the AWS queue event triggers the Lambda, it goes through this record handler. Handler looks at the event. It makes the call on what is it a balance event? Is it a transfer? We added this reconcile transfer, which was to handle the IBS instance where it's a real-time core, but since we're not getting a real-time ID back, we have to go and see, hey, did this transaction actually succeed? And the 2 biggest things we had to do here were actually pull the config and the logger out so we can use dependency injection. By pulling that out, we made it so that the config is no longer part of the environment. And since I don't remember if I mentioned this, but in Kubernetes, since every tenant had their own container for these API adapters, we were able to just use environment variables there, which isn't going to work in Lambda because now we have 1 Lambda running for all core adapter, or for all tenants on that specific core adapter. So now we're going to store config inside of the configuration store. So this is the container. The user makes the API call, say, hey, transfer the money, and it goes into the message queue. Message queue triggers the Lambda. The core Lambda says, okay, you're tenant X. I'm going to grab that configuration. We'll spin it up. If it's a transaction, we're going to go see if this has already happened. Otherwise, we'll pass it on to the core adapter, or to the core. The middleware, the only change is that it's now a Lambda. It's not the actual architecture hasn't changed, right? We're making some calls out, but overall, it's still, we have this clear separation. There's the middleware and there's the core adapter. Okay. The original models had, like, they didn't have the dependency injection, right? So we had two ways to make this move. We were in two separate Git repositories, so we could have updated the model to take dependency injection. It's running in, update Kubernetes to run dependency injection, and then back at the core adapter, in the Lambda, we could basically install the model from the Kubernetes version and use that model. Instead, we just copy pasted. Like, we did all the architecture changes over in the base, or over in the Kubernetes model, and we let it run for a couple weeks just to confirm that everything worked properly. Once we were sure it worked properly, we swapped it over to Lambda using the same model code. And we added this is that transaction history filter. So the middleware knows how to check for idempotency. It knows that, okay, I've got this transaction, here's a unique ID that I'm expecting to see. I'm gonna pull out all the transactions and look for it in that system. The model, the base adapter model knows how to get those transactions. So the two work together in that way. Oh, I should have looked ahead. I'm not a sports guy. But this quote, it's solid, you know? It's really good. Like, you get those fundamentals down, and the levels of everything you do will rise. My team was joking that our next adapter is going to take -5 months, right? Like, because it just keeps dropping down and down and down. I love that I can hand off this to a junior programmer, and like they can cut their teeth on it and like get experience building against a real API. Wait a second, where are the tests? Huh, I'm missing a slide, but I'll tell you about it. Our developers don't have to write tests. The tests are the same. I mean, that's misleading. All the tests are the same because the balance event coming in for IBS, for DNA, for whichever core, like that's coming out of our API. It's never going to change. So what does change is how the underlying system is mocked. So we have a good balance check, and that they have to go into their, because we're in Python and we're using PyTest, they have to go to their conf test file and they update the mock to say, given a balance file, or given a balance call, this is what should happen. Same thing with transactions. So it simplifies the developer lifecycle as well, because they're not having to do individual tests. They're like, for a known good input, what's the expected output? And they just have to figure out how to mock that model or the API calls to do that. I was going to show you just a nice picture of a VS Code test, but I guess I didn't save it. So that's what I got for you today. I've got time for some questions. So what do you guys got? So the question is, at the beginning when we were doing the DNA implementation and with one developer and it took 9 months, could we have gone faster with more developers? I don't think so. Like the program is so small because we were able to identify 3 endpoints. Right? You need to be able to log in. You be able to do a transaction. You need to be able to query a balance. Like, I guess you could have had multiple people do that, like one for each endpoint, if you will, but I don't think it would have sped you up noticeably. The hardest part of that one was, well, between the flip-flopping of REST and SOAP was actually the VPN connection, which I don't like VPN connections for integrating if I can avoid it. I don't really like the allow lists or deny lists either. So like trust your HTTPS and your username and password, your bearer token. Like, but banks are super risk averse, and so are cores. So that's where we are. Anybody else? Okay, so I think the question is, with dependency injection and loose coupling, where do I get the configuration from? All right. So another part that my team handles is our tenant deployments. So we actually handle deploying out our entire system for every single tenant. So we're knee deep into like configuration as code. And so we set up in Terraform, we use CDKTF, but that boils down to being Terraform. Yeah, right, that's good. We have JSON blobs that are turned into, are stored in this parameter store at AWS. And we actually store them in a directory structure, so it's like live origination / bank name / config, and then there's like /secret /secret1 secret2 whatever, and in the middleware handler, when it goes and pulls configuration store, it pulls everything under the bank's name, turns it all into a dictionary, and glums it all together so that you have a single config, and then passes it to a Pydantic model that then has now like a config model that's checked and confirmed that, oh, you should have transaction codes, or that's not a valid API key, or things like that. Yeah. Anybody else? Okay, so the question is, how do I select which core we're going to be making the calls to, right? At the very beginning, we looked at doing a single Lambda for every core, which, like, we've talked about and gone back and forth, because that's like then you could use config to say this bank is using JExchange. Go load the JExchange model, make your calls against that model. We ultimately decided to split that, so every core has its own Lambda. So then it's still config, but the config is saying any message that is for this bank goes to the JExchange Lambda. Yes, it's parsing the message itself. Well, actually, no, it's not even parsing. It's not parsing. EventBridge at AWS is parsing the message and saying, this is supposed to go to live origination, JExchange, bank name. Yeah.
So in your API, you were talking about how the first implementation you did was real simple because they give you back an ID for the thing that was created. You have to do some workarounds with the other stuff to make sure you're. Can you talk a little bit more about that? It looked like kind of some of that kind of surfaced up to the interface. Was all of that taken care of in the implementation?
Okay, so I think the question is, how do we do item potency if the bank itself, or if the core isn't returning a unique transaction ID? Is that a good paraphrase?
You mentioned you added another method later to check the data that the core had, but then it seems like now the caller in your interface has to understand whether this implementation is, requiring you to use something extra or not.
Okay. Okay. So in the handle transfer function, it gets the event, and the first thing it does is goes to check and see if that's in our item potency database. If it's not there, it's just going to run through and try to transact. Like if it hasn't been tried, because the item potency is also sort of like a status database, like is it pending, did it error, whatnot. If it's in there and it didn't succeed, it's an error state, or it's gone, the time that it was tried is longer than the Lambda timeout, the handler, this function, it goes and it says, it decides that it needs to check and see if that transaction has happened already. And when it does that, it calls the model transactions with the transactions functions of the model with a filter, which is usually date range and sometimes amount. It depends on, again, that varies from core to core. So this returns a generator that then the function inside of here is going through each of those individual transactions and saying, does the reconciliation ID from the transfer I'm trying to make match this transfer or this transaction or the next one or the next one? And if it finds it, then it knows it's finished. If it doesn't find it, then it's going to try it again. Did that answer it? Or did I miss it? I missed it. We can talk after. I think that's it. Oh yeah, sorry. He's trying to cut me off. I've been cut off. Thank y'all. It's nice to meet you. Nice to see you.